Okay, we're coming down the home stretch. So homework 5 was due last week. Most people didn't hand it in, so I hope it's coming along. We still have homework 6, and then the final exam, which may be homework 6. I'm not sure yet, depending on how far I get. Because I want to make it too easy, so I don't know. I thought homework 5 was really easy. Homework 6, there's some theory we got to go through to get there. But the simulation is the same. What do you say? Okay, so in preparation for this stuff, because we're now going from elementary queuing theory to intermediate queuing theory. So I want to start with section 5.3. Which is on page 185. 5.3 starts on page 185. And here there's a simple theorem, and it says that in equilibrium, the distribution of the number of customers left behind in certain systems has the same distribution as the number of customers found. In other words, so far what we've looked at is this. So far we have pasta, which says that if we compare the probability that the system is in state J, that is the fraction of time the system is in state J in equilibrium, with the fraction of arriving customers who find the system in state J in equilibrium, then these things are equal if we have Poisson input. That's the pasta theorem. Now, it turns out that in order to be able to analyze the MG1 system, we have to look at the system from the point of view of departures. So what we did previously was we looked at the system from the point of view of the outside observer, and then we related that to the probabilities from the viewpoint of the arriving customer. Now what we're going to do is we're going to look at the system from the viewpoint of the departing customer, and so I'm going to call those probabilities pi j star. So this represents, in equilibrium, the probability that when a customer leaves service, the number of customers he leaves behind him is J. And the theorem says that for a system whose diagram is a one-step diagram, I'll explain that in a minute, then for that kind of system, the equilibrium departure distribution and the equilibrium arrival distribution turn out to be exactly the same thing. So therefore, what we do is we analyze the system from the viewpoint of departures, and we interpret that as a system from the viewpoint of arrivals or the outside observer if we have Poisson input. Now, this is a rather sophisticated theorem at first. In fact, if you look in the book on page 187, there's a formal proof. And in fact, this is the only place in the book where there's a formal mathematical proof that says that something equals something else. And the reason for the formality here is at the time the book was written, that proof had not been published. And there's an interesting story about that, which is that at the end of this section, there's the place where, as an exercise, you're asked to prove Burke's theorem, the one that says that the output process from a MMSQ in equilibrium is a Poisson process. And the proof that's given there is the proof that Burke gave in his original paper in 1956. Now, if you go through that proof, in the proof, it's required that the pi j stars and the pi j's be the same. He uses that in his proof. He uses it sort of waving his hand saying that that's obvious. But actually, maybe it is obvious, but the theorem itself is counterintuitive. So therefore, you want to make sure that all the steps are correct. Well, it turns out that people didn't really know that this was true. And in fact, this theorem had been stated for special cases. In fact, by rather distinguished mathematicians doing queuing theory. So for example, there's a case in which in the ordinary MG1Q, the state distribution is calculated from the viewpoint of departures. That's what we're going to do. Then it's calculated from the viewpoint of arrivals, which is much, much more complicated. And then the author showed that the two are the same. But in fact, that showing that they're the same is completely unnecessary because, as Burke sort of argued, it's obvious that this is true. But it was never published. So therefore, people started asking him about the truth of this theorem and how you prove it. And so he came up with a proof, but the proof was published internally at Bell Labs. So what that means is at that time, if you published a paper, an internal memo, it could not be quoted by outsiders. That is, maybe they would get a black market copy of it, but it was illegal or against the company rules for someone working for Bell Labs to make these things public. And they could not be referred to in the literature by their internal number, memorandum number it was called. So what Burke did was he published this paper internally for all of the people who wanted to find out if this theorem was true or not. But he couldn't publish it, in a sense, outside, because to publish it outside would be to admit that the proof for his prior theorem was incomplete because it was based on something which required proof. So therefore, this is something that apparently required proof, although I think it's obvious, but apparently it required proof. And so I took advantage of this fact by publishing the formal proof in the textbook because it was not available anyplace else. Of course, I gave credit to Burke because it was his proof, but I couldn't give the cite the actual place where it was published because it was an internal Bell Labs memo. So that meant that for a while I got some citations because the only place that the proof of this theorem was available to the public was in that textbook. That was actually that was in '72 when that first came out. Okay, so why is it obviously true? And the answer is, well, all you have to do is look at a diagram, just like we've been looking at all along, in which we have the state of the system at time t versus t. And we're talking about a system here in which the jumps up and down are one step at a time, called a one-step system, like that. Now, the insight here is that it doesn't matter what kind of system this is. All it has to be is in equilibrium. In other words, it doesn't make any difference what the distributions of times between jumps are. So it's much more general than for any particular queuing system with any particular kinds of service times or arrival process. Because all it says is that if I look at the system just prior to a jump, then sometime later, for every time I jump up from some state j, sometime later I will jump down to j. Like that. Of course, they don't have to be separated by a single transition, but they could be way apart. The point is that every time a customer arrives and makes the system jump up by one, sometime later a customer will leave and he will make the system jump down by one. So that means that over the long run, the fraction of customers who arrive just before you jump up, that is the fraction who arrive and find the system in state J, must be equal to the fraction of customers who, when they leave the system in state J behind them. Okay? So stated that way, it seems to be obvious, but you can see from the book that there's a formal proof, and I think at first people needed this formal proof, although now everybody seems to take this as being standard stuff. So this is 3.3 in the textbook, this equality right here. Okay, so we're going to use this later by finding the state distribution in equilibrium for the MG1Q at departure epochs, and then invoking this theorem to say that what a customer leaves behind is the same thing statistically as what a customer sees when he arrives, and therefore that's the same thing if we have Poisson input as the fraction of time you see that state an outsider sees that state. And so the end result is you can use the p's, the pi's, and the pi stars interchangeably. However, there's a little bit of trickiness here because it'll turn out that when you have a finite number of waiting positions, this doesn't apply, because it'll turn out that in that case, let's say I had 10 waiting positions, for example. That means that a customer can leave the system in state, can find the system in state 11. If he finds the system in state 11, that would mean that the server's busy, all the waiting positions are occupied, and so he would be a lost customer. He would not cause a transition. However, he can't leave the system in state 11 because if he arrives when the system is in state 11, he leaves immediately. So if these jumps have to be separated, then the theorem doesn't apply anymore. And we'll see that, or you'll see that, when you start to do homework number 6. So anyhow, we're going to use this, but it's not very important at this point. So I just wanted to mention it because as we go along in the textbook, I want to sort of do things in order because it makes it easier for you to keep up. And if you want to look at Burke's theorem, it's exercise number 2 on page 188. And since it's in the book it's an exercise, that means it's also worked out in detail in the solutions manual. They want to skip section 5.4. And I want to go on here to the section called 5.6, Laplace-Stieltjes transform. Okay, any questions about that? Okay, we'll get back to that. All right, so now we're talking about Laplace-Stieltjes transforms. (5.6). Laplace-Stieltjes transforms. And the definition of it is given by 6.1. Suppose you have a random variable that has a distribution function f. The Laplace-Stieltjes transform of that random variable, or that distribution function, is given by the following integral. E to the minus st df of t integrated from 0 to infinity. Actually, from 0 minus to infinity, because I want to take into account a jump at the origin if there is one. And I'll call that lowercase phi of s. And this is equation 6.1. So this is a transform, just like the generating function. In fact, it's a generalization of the probability generating function. Because what it does is it says, okay, you give me a random variable with a distribution function, which we call f. I'm going to change the form of that information by multiplying by e to the minus st and integrating. And when I get done, I'm going to get some answer, which is going to be a function of s. There it is. And obviously, if you tell me big F, I can get the corresponding phi. And what the theorems of analysis say is, if you know the phi, you can also find the big F that is the transform of. And what will happen is the same kind of thing that happened with probability generating functions, which is that we're going to transform some equations, and we'll find that the result gives us equations that determine the Laplace-Stieltjes transform, and based on that, we can figure out what the distribution function is that produced it. Or in other words, we can go backwards, we can invert it. And formally, this can be viewed this way. I could say that this is the same thing. A lot of people refer to it this way, as the expected value of e to the minus sx. That is, if this is a distribution function of x, maybe I should put a little subscript here to tell you what random variable I am talking about, then the expected value of the new random variable, which is e raised to the minus sx power, is obviously, if I take the expected value of that, what I do is I take the values it takes, multiply by the probability it takes it, and then add up over all possible values. And we're talking here about non-negative integer valued, non-negative random variables like waiting times. So I don't have to worry about negative values, but I want to make sure that when I perform my integration, if there's a discontinuity at the origin, a jump at the origin, that I catch it. Now, notice that analogous to generating functions, that capital phi of 0 is equal to 1. Because if I plugged in here for s equals 0, that would be a 1. I would simply be integrating the distribution function. So this is like the generating function statement that says g of 1 equals 1, or the sum of the probabilities equals 1. Note also that I can differentiate this. Suppose, for example, I differentiated that. So let me call that value phi prime of s. If I differentiate it, I get the integral from 0 to infinity of minus, I'm going to differentiate with respect to s. So that's going to be minus t e to the minus st df of t. And then if I substitute s equals 0, then this part here would simply become 1. There's the minus sign. So I'll put that minus sign over here and make that a plus. And then you see that what this is in fact the expected value of x. So if I know the Laplace-Stieltjes transform of a distribution function, that means I can calculate its expected value by differentiating it and setting s equal to 0. And if I differentiate again, I would get a t squared, and that would give me the second moment, and so on. And it's analogous to what you did with generating functions. Remember, with generating functions, if you differentiated them, you could get all the moments. Take the derivative of the generating function and set the z equal to 1. Here you're setting the argument equal to 0, but it's the same idea. So the s is just a dummy variable, just as in an ordinary generating function. The z is a dummy variable. It doesn't have any physical meaning. Is there a question?
Yeah, the original phi sub x of s is the integral of e to the minus st df xt.
Right.
How is it that when you take the derivative of that, you still have the integral from 0 to infinity of...
I'm differentiating with respect to s. If I differentiate with respect to t, I'm in trouble because this t and this t are the same thing. So I'm going to differentiate with respect to s, and I can take the differential operator inside the integral sign. Remember, we're talking about functions that are all very well behaved, so we never have to worry about whether we can interchange the order of these kinds of limiting operations. So when I differentiate, all that happens is the minus t multiplies this. So there's the t, there's the minus sign. I'll make the minus a plus, multiply through by minus 1, and then what I have left is formally the expected value. So that shows that if I have transforms, if I take their derivatives and then do something with the argument, I can get all of the moments. Now, a lot of you might be familiar with the Laplace transform. And so it turns out that if the distribution function is differentiable, so I'll write it like this. Under certain conditions, that is if it's differentiable, then this is the same thing as the integral from 0 to infinity of e to the minus st times the derivative, which is the density function, because that's a distribution function, dt. And you recognize this as the Laplace transform as opposed to the Laplace-Stieltjes transform. So if the random variable whose distribution function you're taking the transform of is differentiable, then the Laplace-Stieltjes transform of the distribution function is equal to the Laplace transform of the density function. The density function being the derivative of the distribution function. And so everybody who's a double E knows about Laplace transforms. So all of the theorems that work for Laplace transforms work for Laplace-Stieltjes transforms. The difference here, of course, is that I can take into account functions which are not differentiable. because then this is just an ordinary Riemann-Stieltjes integral. So, for example, oh, and by the way, this derivative statement is equation 6.3 in the book. And in fact, I might as well write down something more general. It's easy to see that the variance, remember, is the expected value of the square minus the square of the expected value. So applying this definition, then it turns out that that's the same thing as phi double prime at 0. That gives you the second moment. Minus phi prime of 0, that's the first moment, squared. Okay, so example. Suppose that x is exponential with parameter lambda. Okay, so then the Laplace-Stieltjes transform of the distribution function of x would be given by the integral from 0 to infinity e to the minus st density function evaluated at t dt, because that guy is differentiable. Of course, it's not differentiable at the origin, but we can ignore that because the jump is 0. It's continuous at the origin. Okay, so this is the integral from 0 to infinity e to the minus st lambda e to the minus lambda t dt. That's the density function for an exponential random variable. Then I can integrate that, but that's easy because I'll simply factor out my lambda, and then I have the integral from 0 to infinity e to the minus s plus lambda t dt. I combine these two guys here. And then what I'll do is I'll multiply and divide by s plus lambda. And then recognize that this is now the integral of a density function of an exponential random variable whose parameter is s plus lambda. So therefore, this integral is simply 1. And so the answer is that if I have an exponential variable with parameter lambda, then the Laplace-Stieltjes transform of its distribution function is lambda over s plus lambda. Now, according to the theory, the inverse is unique. So that means that if I solve some kind of problem and I found out that it contained the transform of the form lambda over s plus lambda, that this would then be the transform of the distribution function of an exponentially distributed random variable. That is, either, I can interpret it either way, it's the Laplace-Stieltjes transform of the distribution function of an exponential, or it's the Laplace transform of the density function of an exponential. Those are the same thing. Okay, so one of the things to keep in mind is that if you see this later, you can go backwards. Okay, what about the case? Let's call this example 1. So let's do example 2. Suppose that x equals a constant, c. Now, the reason that this is important, one reason is that if I'm talking about queuing theory, it'll turn out that answers are often given in terms of the Laplace-Stieltjes transform of the distribution function of the service times. So if I have exponential service times, then I'm going to get this transform. If I have constant service times, then I'm going to get the transform I'm going to write down. And the beauty of the Laplace-Stieltjes transform is this is a discrete random variable. This is a continuous random variable. I don't have to treat them by separate formalisms. I handle them both all the same way. So what's the Laplace-Stieltjes transform of this random variable? Well, let me find its distribution function. So what does distribution function look like? Well, it would look like this. Here is the distribution function of x evaluated at t. We're talking about example 2 now, not example 1. There's t. This random variable always takes the value c. So here's the value c, which means its distribution function would look like this. where this is the value 1. Okay, so now I want to find the Laplace-Stieltjes transform of this random variable, that is, of this distribution function here. So this would be the integral from 0 to infinity of e to the minus st d f of t. But of course you know that this is now just an ordinary Riemann-Stieltjes integral. I see that df of t, the change in f, is 0 everywhere except at the value c. So the way I evaluate this integral is I take the integrand at the jump point and multiply that by the change in f at the jump point, which in this case is 1. It goes from 0 to 1. So therefore, the evaluation of this integral would give me e to the minus sc. So if I saw this as a transform, that means it's a transform of a random variable that is constant with that takes the value c with probability 1. Okay? Okay, let's look at the convolution. If you remember, when we looked at generating functions, we saw that the generating function of a convolution was the product of the generating functions. And now it turns out that the same thing is true here. The proof is more requires more mathematics, but it's the same idea. So for example, suppose I had that f of t is equal to, so let's say I'm going to add up two random variables with distribution functions f1 and f2. So here is df2 of x. Okay, I'm writing this, I'm using the notation and 6.4 in the textbook. So this is the probability that random variable 2 takes the value x, and this is the probability that random variable 1 takes a value less than or equal to t minus x, and then I integrate that over all values of x from 0 to t. So that would give me the distribution function of the sum of these two independent random variables. Okay, now, if I multiplied this or took the differential of that, let's see, I should give myself more room. Let me do that. Here is f of t. Yes? This is f1 of t minus x d f2 of x. So this is the Riemann-Stieltjes representation of the distribution function of a sum of two independent random variables, one of which has distribution function f2, the other of which has distribution function f1. And these random variables don't have to be continuous, discrete, or anything. They can be mixtures. It doesn't make any difference. If I follow the rules for Riemann-Stieltjes integration, then this would represent the convolution of those two distribution functions. So it would give me the distribution function of the sum. So now what I'm going to do is I'm going to take the Laplace-Stieltjes transform of that. All right, so this is it was equation 6.4, but now I'm doing some more to it. So to take the Laplace-Stieltjes transform, I take its differential. So I take the differential of that. Then I multiply by e to the minus st. And then I integrate over all t. Yeah, 0 to infinity. Okay, so you imagine that you evaluate this convolution, and it turns out to be a function of t, and then you take the differential of that, multiply by e to the minus st, integrate, and by definition then, that's the Laplace-Stieltjes transform of the distribution function of their convolution. Okay, now what the theorem says, the theorem says that if you do that, that'll turn out to be a product of two integrals, which you can identify, one of which would be the Laplace-Stieltjes transform of f1, and the other would be the Laplace-Stieltjes transform of f2. In other words, the Laplace-Stieltjes transform of a convolution is the product of the transforms of the individual distribution functions. So it's analogous to what you saw with generating functions. The proof involves being able to manipulate this integral of an integral. So it turns out to be you relate this double integral to an iterated integral, and then you do some stuff. And actually, this stuff is done in the book, but I don't think it's important for our purposes to actually worry about how you carry out this arithmetic. What's important is to recognize that if you do it, that when you get done doing whatever the right-hand side indicates, it can be observed to be a product of two functions, one of which is the Laplace-Stieltjes transform of that distribution function, and the other is the Laplace-Stieltjes transform of that distribution function. So that's going to make things simplify with respect to distribution functions and Laplace-Stieltjes transforms, just the way generating functions simplified with respect to non-negative integer-valued random variables, because instead of having to perform complicated convolution, all I have to do is multiply their functions. Okay, that's it given by equation 6.5. Actually, you can prove that in an easy way, although it's deceptive because there's a step in the proof which is obvious but actually requires proof if you really care about these things. Because suppose that x, that's the random variable here, is equal to x1 plus x2. X is the random variable that this is the for which this is the transform of its distribution function, and likewise this one here and that one there. Okay, now if I wanted to find the Laplace-Stieltjes transform of the random variable x, then by the definition I could view that as the expected value of e to the minus s x1 plus x2. Remember, formally, although I erased it, it was right here before, the definition of Laplace-Stieltjes transform right here is the same thing as the expected value of e to the minus sx. So if I have, if x is equal to x1 plus x2, its transform would be e to the minus s x1 plus x2. But that's the same thing as the expected value of e to the minus s x1, e to the minus s x2 by ordinary arithmetic. And now comes the big step, but which is sort of obvious, even if you've never seen it proved, I'm sure you believe it, which is that if x1 and x2 are independent, then the expected value of a product is the product of the expected values. E to the minus sx1 is a random variable. E to the minus sx2 is a random variable. So if if x1 and x2 are independent, then e to the minus sx1 is independent of e to the minus sx2. So by independence, I would say that's the same thing as the expected value of e to the minus sx1 times the expected value of e to the minus sx2. But by definition, that's the Laplace-Stieltjes transform of x1, and this is the Laplace-Stieltjes transform of x2, and so I've proved it. Of course, the proof that if the random variables are independent, the expected value of the product is the product of the expected values, that really includes in it the arithmetic that I didn't do here. But it seems sort of reasonable. Everybody knows, for example, that the expected value of a sum is the sum of the expected values. So it's not unreasonable. that the expected value of a product is the product of the expected values, at least if the random variables are independent. Okay. Now, there's another interesting aspect of Laplace-Stieltjes transforms. And this one is peculiar to queuing theory. And this is stated on, starts on page 198, section number 3. And the idea is this. Okay, so page 198. Suppose I have an interval, which is a random interval. So to be concrete, let's make that a service time. And during that service time, during that interval, customers arrive according to a Poisson process. Now, obviously, if I know something about the length of the interval, then I know something about how many customers arrive. And if I know something about how many customers arrive, then I know something about the length of the interval. So the question is, what's the relationship between the distribution of the number of Poisson arrivals during the random interval and the length of the random interval? So let Pj be the probability that during this interval I have exactly j customers arrive. So what is that? Well, if I call the interval's distribution function f, then df of t is the probability that the interval lasts exactly t. And now, conditioned on the interval lasting exactly t, I'll multiply that by the conditional probability that during that interval I have exactly j arrivals. But if they arrive according to a Poisson process, all that matters is how long the interval is. So if the interval is of length t, the probability of exactly j arrivals would be lambda t to the j over j factorial e to the minus lambda t. And then I would integrate that sum over all possible values of t. So that's just a theorem of total probability. So that's the obvious relationship between the distribution of the number of Poisson arrivals during an interval whose distribution function is big F and big F. Okay, now what I want to do is I want to calculate the generating function of P. Remember, this is a non-negative integer valued random variable. So let me call the generating function g of z. Okay, so g of z is equal to, by definition, the summation of p sub j z to the j, summed as j runs from 0 to infinity. So now over here, that's the sum of the integral from 0 to infinity. Here the sum runs from 0 to infinity. Lambda t to the j over j factorial e to the minus lambda t df of t. And now I do the obvious, which is I interchange the summation and integration sign. So I get the integral from 0 to infinity of the sum as j runs from 0 to infinity. And I forgot to multiply by z to the j. Okay, so that's z to the j, that's the z to the j. And now what I'm going to do is I'm going to take this z to the j and I'm going to combine it with a lambda t to the j. So that means that I'm going to have the sum of lambda t z to the j over j factorial e to the minus lambda t df of t. Everything works out so neatly here because of the assumption of Poisson arrivals. Okay, now I take this sum right here, and I recognize, as we've seen 1,000 times now in this course, well, maybe not 1,000, maybe 3, but approximately 1,000, that this is the same thing as the Taylor series expansion e to the plus lambda tz. So therefore, this integral becomes the integral from 0 to infinity. Notice that I'm careless about the minus sign. I don't have to worry about that unless I'm actually evaluating this thing and want to capture a potential jump at the origin. Okay, so I've got the integral from 0 to infinity. I have e to the minus lambda t, e to the plus lambda tz. That's e to the minus lambda minus lambda z t df of t, if I did my arithmetic right. So e to the minus lambda t, e to the plus lambda zt. That's what I got. There's my e to the minus lambda t, e to the plus lambda tz. But what is that? Well, this is of the form integral from 0 to infinity of something, e to the minus something, t df of t. So that, by definition, is the Laplace-Stieltjes transform of the distribution function f evaluated with s equal to lambda minus lambda z. Okay, so there's our important result. The generating function of the distribution of the number of arrivals that occur according to a Poisson process during a random interval whose distribution function is f is given by the Laplace-Stieltjes transform of that distribution function evaluated at lambda minus lambda z. This is equation 610 in a textbook. Okay, so let me write it over here. Okay, so here are some of the things we know. The Laplace-Stieltjes transform of a sum is the product of the transforms. And we just found here is that the generating function of the number of Poisson arrivals during a random interval is equal to the Laplace-Stieltjes transform of the distribution function of the length of that interval evaluated at lambda minus lambda z. Or equivalently, that's the same thing as saying that g evaluated at lambda minus s over lambda is equal to phi of s. In other words, if I simply set lambda minus lambda z equal to s and solve for z, then I get this equation right here. So I have a simple correspondence between the generating function of the number of arrivals and the Laplace-Stieltjes transform of the length of the interval. Okay, so now we're getting somewhere. So any questions about that? You look like you have a question, but you're afraid to ask.
I don't know where to ask.
You don't know where to ask.
Yeah.
Okay, all I'm doing is setting up some theory that is going to make the coming theory easier. And what this does is it means that you don't have to do a lot of calculations, a lot of things that look like they might be calculations. Actually, everything collapses. So once you get to it, it's not at all bad. All right, so now I want to go on to the next section, which is called Renewal Theory. Actually, the name of the section is Some Results from Renewal Theory. And renewal theory is a subject in itself, and a renewal process is something we've already seen in homework 2, in fact, where you have intervals and you interrupt intervals at random, an interval at random, and then you ask things about the distribution of the interval that you interrupted. So you did this in homework 2. So let me remind you. This will turn out, as you'll see shortly, to be very important. Okay, so in a renewal process, what you have is you have intervals. The intervals, for example, these could be arrival intervals. And then you have the intervals interrupted. Actually, what we did is we looked at it this way. We said, here's 0, and here's some time t. And then we generated these intervals by saying that we had arrival. So there's an arrival, there's an arrival, there's an arrival, there's an arrival, and so forth. And the inter-arrival times had distribution function were selected from a population we called X. And then the question was, well, what you did in that homework was you drew these X's out of the urn, and you called the first value X1, and then the second one X2, and so forth. And you kept on doing that until for the first time you got an interval that covered this arbitrary point T. So you picked out an interval at random. And then you said, okay, now let's call that interval that you picked out I. Actually, the I is one of the X's. It's the last X you pulled out of the urn before you stopped sampling. And then we said, now let's call the first half of the interval A for age, and the second half R for remainder, and let's calculate the expected value of R. Now, in the context of queuing theory, these intervals could be service times, and this T could be an arrival. And then the question I want to ask is, if a customer arrives in the middle of a service time, how long does he have to wait for the end of the interrupted service time? Because in an MG1 queue, in a single server queue, everybody who arrives either arrives when the server is idle or when the server is busy. If the server is idle, there is no interrupted service time. If the server is busy, then some service time is interrupted. And the waiting time of the arriving customer is going to depend on how much time remains in the service time that he interrupts. So we want to find what the distribution of that is. So what happened is, here was the result that we gave in homework 2. Okay, now by the way, this is called a renewal process if the intervals are independent, identically distributed random variables. And the remainder is called the renewal interval. And so this subject is called renewal theory. And actually there's quite a bit to it. And so this is just an outline of some stuff done in the textbook. I'm going to try and do the same stuff more easily here. Less rigorously, more easily. Now, I claimed was that the expected value of the interval I was equal to the expected value of X plus the ratio of the variance of X to the expected value of X. And the expected value of R, obviously, is 1/2 the expected value of I. The surprising thing was that even though the I is one of the X's drawn out of the urn, it doesn't have the same distribution as the X's. It's biased to be larger than a typical X, and the amount of the bias is the ratio of the variance to the mean. And you checked this in homework 2. And you saw, for example, that if the X's are exponentially distributed, then the variance is the mean squared, so the variance to mean ratio is the same as the expected value of X. And the average I would be E of X plus E of X, or 2E of X, which is what the Markov property predicts, although most people still guess the reverse. Also, if the intervals are constant, then the variance is 0. Then the average I and the average X are the same. But the only time that happens is when the intervals are constant, which means when there's no variability. But whenever there's any variability, then the average interrupted interval is larger, biased towards the large size of the distribution of the X's. All right, so this turns out to be important for the reason that I said, which is that in queuing theory, when a customer arrives, if he's blocked, he must arrive during somebody's service time, which means that the service time that he's interrupted tends to be larger than the service times that are typical. And his waiting time is affected by that, so we want to see how that all works. Okay, so it turns out that there's a simple answer to this, and I'm going to try and give an intuitive derivation. Okay, so let me put it over here. This is equation 719 on page 205. And what it says is this: let f sub I of t be the distribution function of the length of the covering interval. Now, what's the relationship between the distribution function of I and the distribution function of x? And the answer is that the differential of the distribution function of I is equal to the differential of the distribution function of x times t divided by e of x. Okay, now in the book, that's proved using the renewal theorem or something like that, relatively complicated result. But I think once you see this result, you can reason from it intuitively and understand what's going on. This says that in this process, the frequency with which intervals of length, intervals I of length t occur is given by this probability. In other words, the probability that if I select an interval according to our process, okay, what is that now? I've got these intervals, and I'm going to arrive at random, and in the process, that's the t over there, in the process I'm going to pick out an interval, and I'm going to call that I. Now this says that the frequency, or the probability, that the interval that I pick out is of length t is proportional to two things. It's proportional to the length of the interval. It's also proportional to the frequency with which intervals of that length occur. The denominator is just a normalizing factor. So imagine that I'm looking at this process, and first of all, I'm going to fix the frequency. So now I'm looking only at x's whose length is t. I'm going to ignore everything else, and I'm going to look at the times when my random arrow picks out intervals of length t. Well, if I'm looking only at intervals of length t, then the probability that I pick one out that's of length t should be proportional, should be equal to the frequency with which intervals of length t occur. So if I'm going to fix t, the probability that I pick out an interval of length t is equal to the frequency with which intervals of length t occur. Because remember, all these intervals are these x's. On the other hand, suppose that I fixed the frequency and just asked for a given frequency of intervals of length t, then the probability that I will pick out an interval of length t is proportional to the length of the interval. All other things being equal, intervals that are twice as long as other intervals are going to be picked out twice as often, because I'm picking them out at random by simply picking a point in time. So by that argument, this frequency should be proportional both to the length of the interval and the frequency with which intervals of that length occur. Now, since this is supposed to be a distribution function, that means that it must integrate out to 1. If I were to integrate this, then you would see that what I'm integrating would be, this is a constant of course, the numerator when integrated is exactly the expected value, and therefore the numerator and denominator would cancel, would give me 1, and well, let me write it down. The integral from 0 to infinity of dfi of t. That must be 1, because f is a distribution function. What is that? Well, that would be 1 over e of x integral 0 to infinity t dfx of t. But of course, that by definition is the expected value. So what I would get is expected value over expected value, or 1, which of course is what I must get. So my point is that that this equation says that the probability that the interval length is t is proportional to the product of the length of the interval and the frequency with which intervals of that length occur. And the denominator here is a proportionality constant, because with the denominator given by e of x, then it turns out that this integrates out to 1, and so therefore that's the proportionality constant. Okay, so this will turn out to be an important result. Now, I'm doing things quickly. All I'm trying to do here is convince you that these formulas are true. To actually derive these things rigorously, you have to go through more work. But I think that they're believable, and this is not a course in stochastic processes, so I don't want to get too bogged down in the mathematics such that we never actually get to the queuing theory. Okay, let me erase this. And by the way, are there any questions before I erase? I'm getting better at not erasing before I say, are there any questions? But there are no questions. There's a question?
All you're doing is you're replacing the dfxt with the upper equation and applying the theorem.
Here. Yeah, all I'm doing is I'm trying to justify this. So what I'm saying is that this probability is proportional to that, and so there's a proportionality constant. So I'm writing the proportionality constant as 1 over the expected value. And the reason that that's the proportionality constant is that the whole thing has to integrate out to 1. And so if I call the proportionality constant 1 over the expected value, then by this thing here, it integrates out to 1. Okay, so therefore, I could have written this as c and then said find the value of c that makes this a distribution function, and then the answer would be c must equal 1 over the expected value. Okay, so now suppose I wanted to find the expected value of I. So by definition, that would be the integral from 0 to infinity of the values that I takes times the probability that it takes those values. So this is the differential of the distribution function of the covering interval I. Now I plug in what I know df of I must be. So what I get is 1 over e of x, that's this guy here, integral 0 to infinity. When I multiply this by t, this becomes a t squared, dfx of t. But what's that? Well, by definition, that's the second moment. So this becomes the expected value of the square of x divided by the expected value of x. So this is straightforward. The truth of this statement, that that is equal to that, depends on this statement right here. So I want to emphasize that this is derived in the book through a semi-rigorous argument. You can look it up in other books on the subject of renewal theory, but it makes perfect intuitive sense. And if you look back at homework 2 and look at the example that I did when I did an intuitive argument to get the answer that these formulas predict, this is exactly what I did. I took the intervals, I broke them up, and then I said that picking out any interval is proportional to the width of that interval. And so in the diagram, you had the width of the interval, and you had it repeated the appropriate number of times, and the end result was exactly this here, except everything was discrete in that case. So rather than repeat it now on using up this time, I suggest you go back and look up homework 2 and look at the example I did in the on the DVD in the lecture for the discrete case that I gave in homework 2, and the argument is exactly equivalent to this. Okay, now continuing on, this thing can be written as the expected value squared of x plus the variance of x divided by e of x. Why is that? Because the variance is equal to the mean, to the second moment minus the mean square. So if I take the second moment, subtract off the mean square, that cancels that, and that would give me exactly that. Okay, so I'm just writing it in a different way. And then that can be written as, dividing this out, that's e of x plus v of x over e of x. And that's the formula that I gave you over here in homework 2. So in homework 2, I gave you that formula, asked you to calculate it for a particular case and compare it with simulation, and of course it worked. Okay, so now I've derived this result, at least if you believe the argument for this result here. Okay, now let me factor out an e of x. Let me write it slightly differently. I'm going to write that as e of x times 1 plus v of x over the square of e of x. So this thing and this thing are exactly the same thing. And so from that, let me go back here and then, well, I'll continue. I guess I have room here. That means, now here's what I want to say, that, let me put it up here. That means that the expected value of the remainder of the interrupted interval, which we already saw by symmetry, is equal to 1/2 the expected value of the covering interval. That's equal to e of x over 2 times 1 plus the ratio of the variance to the square of the average of x. Okay, so starting with this, I get this. Now, let me remind you that when I was talking about the MG1Q, I introduced it by going through the, what was the name of that recursive relationship I gave you? Anybody remember? Lindley's equation, and that was simulated in homework 6 in the stochastic models course. And what I asked you to do was download that and look at it. And on that homework, it states what the Politic-Kinchin formula is for the average waiting time in an MG1Q. And then using the simulation in that homework problem, you're supposed to plug into the, run the simulation and then plug into the Politic-Kinchin formula and show that you get the same values. All right, so the point is that we've already seen what's called the Politic-Kinchin formula, so let me write it down. This is one of the main results of queuing theory. This is that for the MG1Q, we have the following. The expected value of the waiting time is equal to rho over 1 minus rho, where rho is the server utilization, times e of x over 2 times 1 plus v of x over e squared of x. Okay, so this is the famous Politic-Kinchin formula. Actually, it's the mean value version of it. You can actually get the complete distribution, or at least its Laplace-Stieltjes transform, which is also called the Politic-Kinchin formula, and we're going to do that. Okay, so this is the one that gives you all the insight into the MG1Q, because it shows, for example, that as the utilization goes to 1, the average waiting time goes to infinity. It shows you that the average waiting time depends on the ratio of the variance to the square of the mean. And in particular, if the service times, that is, the x is the service time in this formula, if the service times are exponential, then this ratio is 1, the multiplying factor is 2. If the service times are constant, that ratio is 0, and the multiplying factor is 1. So that for exponential service times, for the same utilization, you have an average waiting time that's twice as long as you would have if the service times were constant. And the only difference, therefore, is the variability of the service times. And the interesting thing is that it's for the same row. So therefore, what this says is that in these two cases, the likelihood of having to wait is the same. But if you wait twice as long in one case as in the other. Okay, so this is a famous and important formula. Now, notice that, that this piece right here is exactly the expected value of the remainder of an interrupted service time. Right? Here's the expected value of the interrupted interval. It's right there. If I divide that by 2 to go from the average whole interval to the average partial interval, then I get this result right here. So this says that the average waiting time, I said that the average waiting time, that the waiting time in general, was related to the length of time that remains in the service time that is interrupted by an arrival. But now you see, not only does it depend on it, it depends on this perfectly neat way. It says that the average waiting time is this factor times the average time remaining in the interrupted service time when a customer arrives. So it's really amazing that this renewal theory result would pop up this way. And one of the things about queuing theory is these kinds of results tend to pop up all over the place. And once you begin to understand that and recognize these things, that takes this subject that looks like it's an awful lot of arithmetic and calculation and makes it meaningful because you look at those things as single concepts. So the average waiting time in the MG1Q apparently is proportional to the average remaining time in the service time interrupted by an arbitrary arrival. And that thing is multiplied by rho over 1 minus rho. Why that multiplying factor is that, at the moment we don't know, but I'm going to now, with this argument, I'm going to derive the Politic-Kinchen formula in an intuitive way. So we'll get to the answer right away, although it's not rigorous. I think it's perfectly convincing. Okay, so I'm going to erase this here and then write the argument that's going to give me this right here. So any big picture questions about where we stand here? Okay, so everything fits together like this. That's what I claim at the beginning of the course, and now we're fitting them together. Of course, if along the way you broke some of your pieces, then they don't fit together, but you've got to do the best you can with what you got. All right, so now let me make an argument for why this is true using this interpretation. Okay, so a customer arrives, and when he arrives, he finds a queue in general, then he leaves. We want to find how long he waits. The length of time he waits depends on two things, at least two things. First of all, if he arrives when the server is idle, then his waiting time is 0. If he arrives when the server is busy, then his waiting time is the remainder of the interrupted service time plus the service time of each of the guys in front of him. Each of the guys in front of him has a full service time, and the interrupted service time, the remainder, is a partial service time. Of course, as you already know from homework 2, the partial service time could be longer on average than a full service time. That was one of the strange things because of this variance term. Okay, so now let me express that by simply writing a formula for the average waiting time, E of W. So the average waiting time, well, let's see. First of all, let me worry about the remainder of the service time of the guy in service. With probability 1 minus rho, that value is 0. Rho, remember, is the utilization. So if rho is a utilization, rho is the probability that the arrival finds the server busy, and 1 minus rho is the probability that the arrival finds the server idle. So with probability 1 minus rho, the remaining interrupted service time is 0, because there is no interrupted service time. And with probability rho, the remaining interrupted service time is E of r, given by this thing in the box right there. Now, in addition, he has to wait for the service times of all the customers in front of him. So what's that? Well, let's say that the average service time for each of those customers is E of x, and the number of customers is E of q. Remember, I'm just making an intuitive argument using expected values. Okay, so this says that the length of time he waits is equal to the number of people in the queue that he finds times the service time of each of those people plus the remaining service time if in fact he arrives during a service time. If he arrives when the system is empty, which occurs with this probability, then he waits 0. Okay, now I'm going to just change some stuff here, substitute some stuff here. Let me recognize that E of q, by Little's theorem, that's equal to lambda E of w, by L equals lambda w. This is the average number in the queue. This is the rate at which they enter the queue. This is the average time they spend waiting in the queue. Now, lambda E of x, of course, is equal to rho. So let's rewrite this. The expected value of the waiting time is equal to, that term is 0, rho E of r plus lambda E of x, okay? That's the arrival rate times the average service time. That's rho by Little's theorem. So this becomes lambda E of x is rho E of w. Well, now I solved this for E of w, and what I get, this is simple enough. I solved this for E of w, and what I get is E of w is equal to rho over 1 minus rho E of r. But what's E of r? E of r is the remainder of the interrupted interval, the service, interrupted service that's in progress when the test customer arrives. And we already argued separately that that value is given by this. And that's the Politic-Kinchen formula. Is there a question?
Yeah, in the equation, in the third equation at the bottom, EW equals 1 minus rho 0 plus rho ER.
Right, this is the key. But it's not rigorous. So that means that the fact that you don't understand it, either that means that you're too dumb to understand it or too smart to understand it, right? Because it's not a rigorous argument. So a mathematician would say, wait a minute, that doesn't make any sense.
No, there's only one question I had about it.
Okay.
The first term is to represent the chance that it finds the system empty times the value that it weighs in that case.
No, actually, no. This represents this piece right over here. I'm talking about the interrupted service time. So there's two possibilities. When I arrive, either there is no service time and I wait 0, or there is a service time and I interrupt it. If I interrupt it, then I have to wait, although I'll be at the end of the queue, I have to wait until that service time finishes. Now, how long does that take? Well, with probability 1 minus rho, it takes 0, or there's nothing to interrupt. I enter service immediately. With probability rho, the server's busy, and in that case, the length of time I have to wait for the interrupted service time to end is E of r. That's an interval interrupted at random in this renewal process. The renewal process is the sequence of service times. So this piece over here tells me how long I have to wait because of the potentially interrupted service time. Then there's the piece about how long I have to wait here.
But you only have to wait that much if in the case where with row probability.
No? Okay. Let's forget about this now. This is the piece, which is actually this piece right here. This is the amount of time I have to wait because of the person in service when I arrive, on average. Okay, now, when I arrive, I'm also going to find, on average, a queue. Now, that queue could be 0. So this is the average queue length. It includes the times when the queue is 0. So if I multiply the average number of people I find in the queue in front of me by the average service time of each of those people, because each of the people who's in the queue, I have to wait their full service time. If I multiply the average number I find in the queue in front of me by the average time each one has to spend in service, I get the total amount of time I have to wait from when I arrive. That is the total amount of time I have to wait to serve that guy, plus that guy, plus that guy, plus that guy, and so forth. So E of x times E of q is the total length of time it takes to serve these guys, and this term is the total length of time it takes to serve the remainder of that guy. And then the rest of it is just easy. So I understand what your difficulty is. And in fact, in the book, I've been more careful about that, but that also makes the argument more complicated. And for a quick understanding, I think that, well, I understand it, so I don't need that more complicated argument. But I did before I saw this, because the way the brain works is that once I think I know what the answer is, it's a lot easier for me to understand it, because I know that I'm thinking to the right conclusion, as opposed to trying to understand something that might be false, because then you really confuse yourself. You convince yourself that something's right by reasoning through, and then someone tells you, yeah, but it's wrong. So what was the mistake in your reasoning? It's like these probability problems with combinatorics, which is that if someone tells you the answer in the back of the book and with powers and factorials and all of that kind of stuff, you can always come up with an argument for why it's right. So I could tell you any answer, and the class would always come up would agree with it. Okay, so here the argument is this. First, let's look here first. First of all, this says, okay, when I arrive, there's a certain amount of service that has to be used up before I enter service. This guy's service time, that guy's service time, that guy's service time, and so forth. On average, how many people do I find on the queue? Well, by definition, it's expected value of queue length. How much time on average does each one require of service? Average service time. Okay, so this corresponds to the queue that I find. Now, what about the server itself? When I arrive, either the server is empty or it isn't. Now, the probability it's not empty is rho.
Right, but I think what's confusing me is that if there's a queue, then the server cannot be empty.
Yeah, that's true. But this doesn't say that there's a queue. It could be 0. This is the average queue length. So when I compute the average queue length, if I actually did this, which we're going to do, but right now I'm getting the answer first. If I actually computed the average queue length, it would include the times when the queue is 0. So this is the average number in the queue multiplied by the average time each of those guys spends in the server. That's one piece of my waiting time. The other piece of the waiting time is the time remaining, if any, for the customer in service when I arrive. If when I arrive the server is idle, there is no time remaining. The probability that happens is 1 minus rho. With probability rho, when I arrive the server will be busy. In that case, that means I'm arriving in the middle of somebody's service time. What's the expected value of half of an interval that's interrupted at random? Well, by our renewal theory result, it's this thing right here. So if I take that, plug it in here, I have the average waiting time with the Politic-Kinchen formula for the MG1Q. So this is a clever argument going back and forth. It uses pasta, it uses Little's theorem, all kinds of things in here. It uses this renewal theory result, but once you see how to piece these things together, you get this very sophisticated and important result by a intuitive probability argument. Okay, now I want to sort of start from the beginning, which is now I want to start looking at what's called the embedded Markov chain. This is what I'll do next time. And what I'm going to do is I'm going to write the equations that are going to describe the states of the system from the viewpoint of departing customers. And I'll explain why I need to do that. But when I do that, that makes everything, relatively speaking, simple. And then I will transform the set of equations for the probabilities into the generating function for the probability.